3.
3, got it. Okay. Okay. So let's go from here. We are now recording. Morning. John's here. All right, just a couple of fairly minor announcements. First, believe it or not, wait, sit down. You need to be so you won't fall. I got significant number of amount of grading done over the weekend. Friday was a good day on the Birmingham campus because nobody else was in the office and had few people stopping by. So I got a fair amount of grading done there, but I did have some interruptions. And then over the weekend, it was a pretty busy weekend, but here, there, especially with it rainy like it was yesterday, I got some more done. I probably would have pretty much narrowed the stack all the way down, except my red pen ran out of ink, and I could not find one at the house anywhere. So I then, and Paul, brace yourself for this one too, I got all the Blackboard caught up. So amazing. You should be able to check and see your scores on Blackboard. Now, if you don't see a score for a test on Blackboard and you know you took it, that means I thought you were coming back to finish 1 or 2 problems or as many as you needed. So if you are happy with the score, unfinished score, let me know and I'll put that score in, because I have them graded, marked, but I don't have all of them entered. And if it's a very low score in there and you thought, no, I was going to come back, come see me, and I'll let you finish your test if you were going to do any finishing of it, and then regrade that and put in the correct score. So that's where we're sitting there. They turned on the heat over the weekend, and now we go from freezing to burning in here. I guess this is, Dante had something to say about it, didn't he? Okay. In the Inferno. Okay. Morning. Skylar's here. First. All right, good deal. Okay, now the one other sort of sad announcement to make. I know, we're all burning up in here. After freezing for most of the last couple of weeks, we're now way too hot. I hate to break this to you, because some of you may not have realized it yet, but next week is the good news, bad news situation. Next week is Thanksgiving week. Okay, it comes a little early this November. I think we have more weeks after Thanksgiving than we usually do. So that's one side of the good news. The bad news is there are no classes at all next week. Sorry about that. We have meetings Monday, Tuesday, and Wednesday, so we'll be here, but you guys have the week off. Sorry about that, but don't forget what you're doing, okay? You get over it. Okay. Now, as it's going to work out, I'm afraid, we're going to finish 2.5 today and get started in 2.6, which means we could easily be very close to, if not finishing 2.6, Thursday, which means then Tuesday when we get back could be Chapter 2 test. It just depends on whether we can finish 2.6 Thursday or not. So, hate to have that big a break in between, but hopefully you'll manage that fine. All right, any questions on anything we've done so far? Okay, we are in 2.5, very last page of the section of 2.5, page 161, and this is applications of finding zeros of polynomial functions. So let's turn to that. Here's example 12 in your text, and on this new slide set that I loaded specifically this term to update it because I had been using the old DVD I thought, well, that is missing a couple things. Well, I got the new one, and it's missing the same thing, so they didn't update this. Reggie's here. All right. Now, I do have another question for you. Hey, he's back. Welcome back. You think you're here for the duration, or will you be for the rest of the term, or just a few weeks? 2 weeks, okay. All righty. Good to have you back. Okay. This is a question for y'all because I haven't seen anything, but I may have missed it because I don't get the same things y'all do. Has anyone heard about student course evaluations yet? Have they published anything about that? Okay. They may wait till after Thanksgiving, but that leaves just a couple of weeks more of class before, to do. So be watching for that when those do come up. All right, so here's example 12 in the text, example 11 on the slide set. You're designing candle kits. Hey, they even changed the words a little bit. In our text, it's you design candle making kits. Each kit contains 25 cubic inches of candle wax and a mold for making a pyramid-shaped candle. I don't know if y'all are familiar with what a pyramid is. Pyramid has some type of a base, not circular, that would be something else, but some type of polyhedron base, and then the sides go up to a point, okay? So the picture in your text, you see some pyramid candles there, okay? You want the height of the candle to be 2 inches less than the length of each of the candle's square base. Remember I said a polyhedron base. This one happens to be a square base. And by saying a square base, what else does that tell you? The four sides are all equal of the base. And then you have the pyramid coming up from there. Kind of like, you see that first row there of the bluish ones, they are square bases, pyramid type candles. They look like their height is taller than the dimension of the base. The next row back there that has a green and a couple blues, those are cones, different kind. And then after that they got stars and other things. But the blue ones are sort of like what we're talking about here. So you want the height of the candle to be 2 inches less than the length of each of the candle's square base. What should the dimensions of your candle mold be? Okay. Ooh. So what are we looking for? Dimensions. Now what dimensions do we have? This is going to be a terrible drawing, so stand by for that. Okay. That's supposed to be a square base. Don't laugh out loud. Okay. Now, coming up to some type of a point here, and I did a poor job there. Here's a triangular side, there's a triangular side, and the one over there is, you can hardly see it, twisted enough so you can see it well. Okay, what dimensions do you see? And, okay, yes, Amanda's here. Okay. So what would be our dimensions that we're looking for to this? Z? Okay. Right. Good deal, everybody. Okay. What would be the dimensions that we would need to determine to answer that question? What should the dimensions of your candle mold be? Any ideas? Make a guess. Okay? They actually name them in that first sentence of the second little paragraph there. You want the height of the candle, that's a dimension, to be 2 inches less than the length of each side of the base. There's the other dimension. Normally it would be 3 dimensions, but because it's a square base, those two on the bottom are equal. So since y'all aren't saying anything, let's me name this the L, back there is an L, and over here is an L. This will be the height. Okay? Now I said L. If y'all prefer a different dimension for the base, I'll label it that way. What would you like to use? L okay? Is H okay for height? Okay. So if we can determine L and H, we can give the dimensions of the candle, okay, or the candle mold. But which of these do we know the least about? The length of the side of the base or the height? Which do we say again? The length. We know less about the length because we know something about the height, don't we? Right here. The height of the candle is to be 2 inches less than the length of each side. So we don't know things about the length, but we do know the height is 2 inches less than that length. Okay? So let's take that sentence right there, using the variables I just named, H, height of the candle, to be, or not to be, no, that's the same as is or equal to 2 inches less than the length. How do I phrase that mathematically? L minus 2, excellent, okay, L minus 2. You start with the length and subtract 2 from it because it's 2 inches less than the length. Perfect. Okay, so there we've got that. Now the problem is, okay, what we have up here, each kit contains 25 cubic inches of candle wax. Okay, what does cubic inch measure? Anybody? Ah, here it is. Keegan. What does cubic inches measure? What type of quantity? Anybody? Make a guess. Certainly not measure a length. A volume, exactly. Now here's the rubbing point. Does anyone know the volume of a pyramid with a square base? Really doesn't matter what the base is, the formula. Ha! Thank goodness for the back of the book, right? The back of the book, back inside cover, okay, you have, and this, I assume this is in the ebooks too, but finding it, I don't know how to tell you to do that. But back inside cover of your text, you will not see a pyramid. You do see a cone. And basically the cone's volume is exactly the same as a pyramid. Okay? If you look at that third block down on the right-hand side, it said volume is equal to AH divided by 3, okay? Or 1/3 the area of the base, that's what the A stands for, times the height. That's it for a pyramid as well. My pen got stuck. Okay? So the area of a pyramid is 1/3, I'm sorry, the volume of a pyramid, I got area in the brain here. It must be a Mondays on a Tuesday this week, isn't it? Okay. All right. 1/3 the area of the base times the height. That's the volume for any pyramid. Okay? Now, we have, what is the area of our base? What is the area of the base of that pyramid? Second?
We don't know yet.
Well, we have, second? L squared. Exactly. We don't know what L is, but we know it's L squared. The length squared. So this will be 1/3 L squared. And what's the height? L minus 2. Perfect. Okay. I think we can go to town on this one, can't we? And we know what the volume is, 25 cubic inches of candle wax. So let's plug in the 25 here. Okay? Now, how would you proceed to solve that equation? What's sort of messy about it? Nothing much too messy, but a little bit. Yeah, the 1/3. Yeah, I know y'all love fractions, but you know, if I can avoid them, I try to. Okay. All right. Come on, Evan got it. Can you get in there? Okay. All right. Good deal. Okay. So, how do we get rid of that 1/3 over there, which is sort of messing up the right-hand side? Multiply both sides by 3. And what's 3 times 25? 75 is equal to, and 3 times 1/3 is 1. And let's distribute in the parentheses, and what do you have? L cubed minus 2L squared. Okay? Now, what would you do with that? Any ideas? If we didn't know what we were solving here, and that was the problem in the book, what would be the first thing you would do? The second or third thing you do. Okay, give me something to do.
You do something with the 2L squared?
A little bit, but actually, when you have a higher order polynomial, what form do you want it in? You want everything on one side, 0 on the other side. So, what's that? Yeah, so subtract 75 from both sides. Excellent. Okay, now, I really don't have much room, so let me go up here. L cubed minus 2L squared minus 75 is equal to 0. All right, what you reckon we're going to do with that? I know it was a long weekend, okay? But how do we go about solving problems like that? Certainly not something I can factor. So that's sort of out of the question. What would be your guesses? What's that?
Synthetic.
Okay, we're ultimately going to do some synthetic division. What's going to lead us to that? Tell us what to divide. Can you be rational about it? All right, here's Dimitri.
So you gotta find the possibility.
The possible rational zeros, and what will they be? Yeah, well, it probably will be fewer than you thought.
Yeah.
It's going to be form P over Q, where P is what?
Negative 75.
Okay, all the possible factors are 75. You don't even have to worry about the sign here because we're going to put plus or minuses everywhere. So what would that be?
1.
Plus or minus 1?
5.
How about 3? Plus or minus 3? Plus or minus 5? Any others? 25. How about 15 though? Plus or minus 15, and plus or minus 25, and plus or minus 75. Okay, it is quite a few. Okay, but what's the denominator? plus or minus 1. So we don't even have to really fiddle with that. We're just going to use those numerators. Now, if we think we've been living really well, what would be the easiest thing to check first? Is that going to work? Try it. Plug in L equal 1 over there and see what you get. Minus 76. I don't think that's a 0, is it? Nope. Okay. Forget about 1. Plus 1 anyway. So now we go to Christian's synthetic division. And we don't have much room to write it, so is it okay if I erase that bottom part of the thing here? My beautiful pyramid, I guess I can do it, and all the other stuff down here. Is that all right? Y'all got it? Okay. Well, whether you do or not, here it goes. All right, let's try our synthetic division down here. Oh, my beautiful work. Okay, get over it. Okay. All right. So let's try minus 1. You want that next? I don't think it's going to work either, but let's try it. What goes inside? 1. Negative 2. 0. Very good. Negative 75. Here you do have to watch out for your signs. Skip a line, draw a line. Bring down to 1. Negative 1. Negative 3. 3. Say again. 3. Hey, Cameron's here. Doesn't work, does it? Okay. And Ashley's here. Okay. So, negative 1 didn't work either. Positive 1 didn't work. Negative 1 doesn't. Do I need to carry any further? You see that won't work. Negative 1 times 3 is negative 3, and that doesn't add up to 75. So we're going to forget both of our 1s here. Okay? So let's erase that, and those two. The initial 1 is going to be the same no matter what. What you want to try next? 5. He jumped right over to 5. Okay, JT came in, so it must have been a good idea. Pardon me?
I have a doctor's appointment. I was in red Friday night. I have a concussion.
Oh, sure.
I have a concussion.
I'm sorry.
So I'm going to go to the doctor.
Okay.
Call back from him.
Okay.
So I was blown up. So,
Okay.
is there anything that I need to know?
Everything. Yeah, no. Okay, just take care of yourself. There's no quiz today. I'm not giving out anything. We are in 2.5 now. We should be starting 2.6 before the day's over. And 2.6 is the last section before the test. So we may finish 2.6 on Thursday, which means we could have the test either Tuesday or Thursday of the week after Thanksgiving.
Okay.
Sorry about that. You missed a week of class. So gives you time to recover. Okay. All right. Yeah, you do better. Get better. All right. He wanted to try positive 5. You're all okay to go do that? Now, here's one of the disadvantages of doing this. If we have an upper bound situation, we may hit it here, and we find out we could have hit it in 3, but let's try 5. What goes next? Say again?
I forgot that 3 was one of them. I would bring that.
Oh, you want to do 3?
No, that's fine. I just forgot that we had it.
Oh, okay. You're just leading me astray, huh?
Yeah.
Okay. 5 will give you what?
3.
Say again?
3. It'd be 5.
5, 3, 15, 15, 75. Look at that. Did he look at the book or what? Okay. All right. That does work. So our one possible root is x equal 5, or L equal 5. So there's one possible root, L equal 5 inches, okay? But what does this, okay, now, time out here. If this were a regular math problem, well, we'd be stopping now anyway. But if this were longer, had more things in it, and we wound up with all positives down here with a positive here, what does that tell you? This is an upper bound. Don't try 15, 25, or 75. They're not going to work because that is an upper bound. Nothing beyond that is going to work. Okay? So another good reason to choose it. Okay? Now, what do we do with the bottom? What does that represent? L squared plus 3L plus 15 equals 0. Anyone think you might be able to factor that? Anybody? Anyone at all? If you could factor that, then you'd have some L and L would be the first factors on the first numbers on each factor, and then you'd have to have two numbers that multiply to be 15 and add the 3. Can you think of any two numbers that multiply to be, and they got to be positive, okay? If they were different, that might work. These are both positive. No, it's not going to factor. What do you think might happen if you try the quadratic formula? Let's see, Patrick's not here to suggest it for us. He always suggests the quadratic formula. If you tried that, remember what is in the radical? Minus, the square root of b squared, 9, minus 4ac. 4 times 15? 60. Minus 60. 9 minus 60, negative number in the radical. No real solutions there. Okay? Those would both be complex. We're not going to build a candle with complex dimensions, okay? With imaginary dimensions that may blow up. We don't know what would happen. So, those are out. So it looks like to me that L equal 5 is the length of that base. So L equal 5 is the length of the base. What is the height of the candle? 3. H equal 3. Okay? All right. Okay. Got it. Okay. Now, let's just do a quick think on this. Since I've already erased it, so I'm going to have to write it down. The volume of a pyramid is 1/3 the area of the base, which would be 25, times the height, which is 3. 1/3 of 3 is indeed 1. 25 is indeed 25. Okay, yeah, that works. So we checked it. That does work. Sort of a flat, squatty little candle there, but maybe it's very attractive in some cases. All right, let's see how they did it. Any questions on this? See, all your tools will work. That's what we've been doing, gathering tools, putting them in our belt so that we can solve these problems. So let's erase all this. Let's see how they did it. The volume of a pyramid, they gave it to us, is 1/2 its base, the area of the base times the height. In the back of the book it had A, but they used capital B. Either one is work. I've used the B more. Where B is the area of the base and H is the height. The area of the base is x squared. Oh, they didn't tell us that. They chose the length of each side to be x. We chose L. Doesn't matter. X squared. The height would then be, just like we did, the height of the candle is 2 inches less than the base. That would be x minus 2. So they proceed. The volume of the pyramid is 1/3 x squared times x minus 2. The volume is 25 cubic inches of wax. And so if you have 1/3 of x squared times x minus 2 is equal to 25, then we have an equation we can go with. And they did the same thing we did without telling you. Well, they did tell you. multiplied each side by 3, so you don't have to mess with the fractions. Though you love your fractions, then that gives you 75 is equal to x cubed. They distributed to x cubed minus 2x squared. And then in order to solve this, we need to write it in standard form. Decreasing order of the powers, and that would be 0 is, they put the 0 on that side, 0 is equal to x cubed minus 2x squared minus 75. All right. The possible rational zeros, exactly what we went to next, plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, 25, and 75. And it says use synthetic division to test some of the possible solutions. We tested without synthetic division plus 1. It didn't work. We did minus 1 using synthetic division. It didn't work. And then we skipped the plus or minus 3, thank you very much, and went to plus 5 and found out it did work. Note that in this case, it makes sense to test only positive x values. Why? Second? No? Okay, more reasonable than that. Okay? Candles, yeah, a dimension of a candle can't be negative, right? So forget about the minuses, okay? Earlier, yeah, well, never mind. But you can only deal with the positives. I threw in the minus 1 just to show you it wouldn't work. But only choose the positive because the dimensions can only be positive, okay? And then they sure jumped right to x equal 5 or L equal 5. We did. And sure enough, it worked. Okay? The other two solutions that satisfy that quotient, imaginary, they can be discarded. We don't have imaginary candles. Okay? So you can conclude that the base of the candle should be 5 inches by 5 inches. The height should be 5 minus 2, which is 3 inches. And you can check that. I don't know if they do. This is not the rest of the problem. They ended their problem right there. Okay, they didn't go back and check it. That was example 7. But this is the paragraph at the bottom. Before concluding this section, here is an additional hint that can help you find the real zeros of polynomial. When the terms of f of x have a common monomial factor, it should be factored out before applying the test. Otherwise, you just have bigger numbers, bigger things to deal with, okay? So here's one, for instance, here. What if you have this as your polynomial? F of x is equal to x to the 4th minus 5x cubed plus 3x squared plus x. How do you proceed with that? Factor out an x, because when you factor that out, if you're going to set it equal to 0, x equals 0 is probably not going to be a very interesting thing for a practical problem, with no length at all, or if that happens to be what it is. But whether it is or not, you already know is 0, x equals 0. Then you can proceed with this part and do all your further things with that. And I see right now, just looking at that, what's going to be another root? Real easy one. Just looking at that. X equal. What's the first one we always do because it's the easiest one to check? 1. If you put a 1 in here, that'd be 1 minus 5. That'd be minus 4 plus 3 plus 1 and plus 4. That's going to be a 0. There you already have one. Use this synthetic division on that, and you'll have a quadratic at the end. Factor that. Or use quadratic form. Okay? So, you can see that x equals 0 is a 0 of L. The remaining zeros can be obtained by analyzing the cubic factor. That's a strange way of saying it, but using our techniques, what do we call it? Rational zeros test and all that other stuff. Make sense? All right. That then ends 2.5. All right. Quite a few vocabulary questions at the top of page 162. Let's do those. Number one, the blank blank of blank states that if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the complex number system. Way back at the first of this section. We talked about Gauss in it. And if you turn back one page to that summarized at the bottom of the previous page, don't even have to go back to the first of the section, just one page. The very first summary point. They have 6 points there. What's the first one? State the... That's it! The fundamental theorem of algebra stated by... Was it Gauss or Euler? May have been Euler, I don't remember. Okay, one of those guys. Okay, so that's the fundamental theorem of algebra. Okay, number two, the blank 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 states that if f of x is a polynomial of degree n, which is greater than 0, then f of x has precisely n linear factors. F of x equal a sub n times x minus c1 times x minus c2 times x minus c3 up to x minus cn, where all those c's are complex numbers. That doesn't mean they have imaginary parts to them. They could, because all real numbers are complex numbers too. Okay? Anyone remember what that one is? And the first two words of it are the first two full words on the second line of the question. Oh, my goodness. Ryan's here today. Here we are. Again, you can just turn back that one page, and again, in summary statement 1, it's also listed there. The what? Nope, before that. Number 1. Okay. I'm going to read. The blank 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 states that f of x is a polynomial of degree n greater than 1, n greater than 0, then f of x has precisely n linear factors. F of x. Oh, the linear factor theorem. How did you come up with that? Okay. So that's number 2. This is like pulling teeth. Okay. Number 3. The test that gives a list of all possible rational zeros of a polynomial function is the blank blank test. Rational zeros test. Very good. Number 4. If a plus bi, where b is not equal to 0, is a complex zero of a polynomial with real coefficients, then so is its blank blank, which is a minus bi. Complex conjugate. Perfect. Number 5. Every polynomial of degree n greater than 0 with real coefficients can be written as a product of blank and blank factors with real coefficients where the blank factors have no real zeros. A lot of blanks there. Okay? Now, let's go back to number 2. That describes one of those factors. Number 2, so long ago, we've forgotten. Linear factors, or, and, what's the next up from linear factors? Not that broad. Okay? Linear factors have exponent of what? Maximum exponent. Only exponent. 1. What's next up from that? Yes, and what do we call those factors? We have a formula named that. Say again? Not they are polynomials for sure, but specifically what kind? Maximum exponent of 2. No, that would be just a 2 term. Okay, maximum exponent of 2. if you can't factor this baby, you can always use the quadratic factors. This is pulling teeth, okay. Where the blank factors have no real zeros. Which of those two you just named? Linear, no, the linear always have a real zero, okay? It's the quadratic that don't, okay? Because if they did have real zeros, you could factor them as linear factors, okay? All right, tired of pulling teeth here. Okay, a quadratic number 6, a quadratic factor that cannot be factored further as a product of linear factors, which we were just talking about, containing real numbers, is blank over the blank. Okay. All right. Page 157. In bold under the box. Find the box. Look directly under it. Irreducible under the real, over the reals. Okay. And that's, yeah, number 6. Number 7. The theorem that can be used to determine the possible numbers of positive and negative real zeros of a function is called blank blank of blank. Say again? Anybody? He's responsible for our Cartesian coordinate system. The Cart's rule of signs. Perfect. Okay? And number 8. A real number C is a blank bound for real numbers of F, real zeros of F, when no real zeros are less than C, and is a blank bound when no real numbers are greater than C. Lower bound and upper bound. Perfect. Okay. Homework exercises, do either 9 or 13. They're both, any of the odds, 9 through 13. They're all at Calc Chat, 9's at Calc View. Do either 15 or 17. They're both at Calc Chat. Do any of the odds 19 to 27. They're all at Calc Chat. 25's at Calc View. Do either 29 or 31. They're both at Calc Chat. 29's at Calc View. Do either 33 or 35. They're both at Calc Chat. 37 or 39. They're both at Calc Chat. You don't have to do 41 to 45 unless you just want the exercise of doing it, or 47 or 49. They're all good problems. I'm just not going to ask you those on the test. I don't think, anyway. Do either 51 or 53. They're both at Calc Chat. Do any of the odds 55 to 59. They're all at Calc Chat. 55's at Calc View. Do any of the odds 61 through 71. They're all at Calc Chat. 69's at Calc View. Do any of the odds 73 to 77. They're all at Calc Chat. Do any of the odds 79 to 85. They're all at Calc Chat. 83's at Calc View. Pardon me? It is. But you've done most of them before, remember? Yeah, I thought you had. Okay. Because we've done all those that we've named so far before. Okay. So either 87 or 89, they're both at Calc Chat. And I believe, and then do either 91 or 93, they're both at Calc Chat. I think this is where we start off from today. So these are the new ones. 95 or 97, they're both at Calc Chat. 99 or 101, they're both at Calc Chat. And then some of the applied problems, which definitely was today, 103 and or 105. They're both at should be at Calc Chat. There's a true-false 107 that should be at Calc Chat. There's a think about it, and you can think about doing these if you would like, but you don't have to if you don't want to. 109 through 113. Another think about it, 115. Writing in equation 117. There's an error analysis 119. Okay, I really don't care for those as much because they've written something in the book that's wrong. Okay, so, but if you want to do that, you certainly can. There's another, think about it, 121, and then there's writing an equation 123. All those should be at Calc Chat if you want to do some of those. Those at the end are a little more esoteric. So you decide whether you want to do those or not. All right. Any questions on 2.5? Okay. Remember the test, when we have it, will be the first page will be somewhat similar to the quiz. Okay? Which maybe is a good place, segue for doing this. I was, as I told the people who were here earlier, I finally did get all your grades in Blackboard. Okay? And sort of a sad bit of information was there weren't many paper grades to put in Blackboard. 2 out of my biggest class all term. 2! And we've got less than a month left of class. Okay? Please, folks, don't forget about your research papers. Okay? Now, your quiz 1, most of the people who have not turned that in are not coming to class much. I know a couple of them dropped, though there's one person who is here who hasn't turned it in. Okay? But I need those in, folks, because if you haven't done the first quiz, that means you haven't done the first test. And again, most of those are people who are not here, not attending very much, though there's a couple people, yes? I'm sorry?
I checked Blackboard and my grades not in.
None of your grades are in?
No, I just,
I did it last night.
yeah.
I'll have to go back and check. I don't know why it's not. Because I had my book. I was telling the ones that were earlier, my red ink pen ran out, so I couldn't finish doing the grading, so I started putting in Blackboard. So I may not have saved it correctly or something like that, so I'll have to check that. I'll try to do it today. Sorry. Okay. But it's still, test 1, once I get the grades in, if you don't see a grade, that means either you haven't turned it in or you left enough blank, I thought you were coming back to finish it. So, anyway, yeah, your grades you should have quiz 1 and test 1 in because they're here in your text. I don't know where they are. Quiz 2, by the way, I have a big 3 people have turned in quiz 2. And if the test is coming up, say Tuesday or Thursday after Thanksgiving, then you need to get those quizzes in so you can see what you missed on that so you don't make the same mistake. Because like I said, the first page of the test is going to be covering a lot of the same material that the quiz was, quiz 2 was. And then the second page, and maybe a little on the first page, will be covering 2.4, 2.5, and 2.6. Though there's not going to be a whole lot of 2.4 in there. All right, so let's move on to 2.6. Okay. Last. Say that again. Say that one more time. The test will probably be the week after we get back from Thanksgiving.
Chapter 2?
Chapter 2 test. Yeah. And you all should have your Chapter 2 quiz, right? Unless you've turned it in, which is only 3 of them. Okay. And I think those 3 are not here. Okay. In fact, I know those 3 are not here. Okay. All right. So, let's get this to current slide. Okay, Chapter 2 is still polynomial and rational functions. 2.1 to 2.5 were all the polynomial part. Now we're in the rational function part. What in the world do we mean by a rational function? And it has nothing to do with gender, by the way. So what do we mean by a rational function? Anybody? What's the first 5 letters of that word? Ratio. And what is a ratio? Something like that, anyway. It's what? What is a ratio? those things you know and love so much.
It's basically a fraction.
Basically a fractional form. A comparison of two numbers in a division sense, which is like a fraction. Exactly. So that's what rational functions are. Here are the objectives. You see there's quite a few. We'll first find domains of rational functions. We didn't have to worry about that with polynomial functions. Why? What was the domain of all polynomial functions? All real numbers. Rational functions may not be that. Okay? We'll find vertical and horizontal asymptotes. What in the world are they? Well, we'll learn if you don't know already. Basically, vertical asymptote is where the function, rational function, is not defined. And what is true about polynomial functions? Defined everywhere. Okay? So we'll introduce the concepts of vertical and horizontal asymptotes. We'll sketch graphs of rational functions. Oh, that should be fun. And it is. And we'll sketch graphs of rational functions that have slant asymptotes. We're going to skip that part. Okay? And then we'll use rational functions to model and solve some real-life type problems. Okay? So we'll introduce. Okay. Here's what a rational function is. Remember, it's a ratio of two functions. What kind of functions are they? Polynomial functions. Okay? A rational function is a quotient or a ratio of two polynomial functions. Can be written in the form f of x, the rational function, is n of x, which is the numerator polynomial, divided by d of x, which is the denominator polynomial. Where n of x and d of x are polynomials, and d of x is not the zero polynomial. Why not? Why can d of x not be the zero polynomial? You can't divide by zero, ever. Okay. Which also leads us to another situation, which we'll get to really shortly. In general, right now maybe, the domain of a rational function of x includes all the real numbers except those x values that make that denominator zero. Okay? So if that denominator is a polynomial function, one of the first things we've got to do is find the zeros of that polynomial. Because those zeros can't happen. Okay? That's going to be where those vertical asymptotes are going to be. Okay? So that's one of the first things we're going to learn to do. Okay, much of the discussion of rational functions will focus on their graphical behavior near those x values that you exclude from the domain. Okay? We'll be doing some things very similar to what we did in behavior to describe that. We'll get there. So here's example 1. Is that a rational function? 1 over x. Yeah. 1 is a polynomial function, a monomial, 1. And x is a polynomial function, monomial x, okay? Yeah, that's a rational function. It says find the domain of that. What would be the domain of that function, 1 over x?
X has to be positive.
Doesn't have to be. It can be.
Well, it has to be greater than 1.
No, it doesn't. It could be 0.5 or 1/3. Okay? Here's the better answer. Okay? We'll say, and this will be almost always, set of all real numbers except where are the things that it can't be? What can x not be? 0. It can be positive. It can also be negative. It can't be 0. Because 0, that function is undefined. Okay? Now, discuss the behavior of f near any excluded values. We only have one excluded value, 0. What is happening to f, the function, when x gets close to 0 from the left? Okay? Let's take it down some. When x is equal to 1, what's f of x? X equal 1, what's f of x? 1. How about when it's 1/2? That's closer, right? What would be f of x? Anybody? 1 over 1/2. Anybody? 2, okay? How about 1 over 1/3, when x is 1/3? Getting even closer to 0. 3, 1/4, 1/10, 1/100th, okay, 1/1000th. Okay, what is happening to f? Getting bigger and bigger and bigger, going to positive infinity. Never gets there because it can't equal 0, but it gets larger and larger as x gets closer and closer to 0, then f of x from the right-hand side, it blows up, gets incredibly large. How about f of x when x approaches 0 from the negative side? Like -1. What's f? -1. -1/2. -2. -1/3. -3. -1/10. -10. Okay, you get the idea? Where is it going there? Yes, getting incredibly large negatively the closer you get. So what does that function look like? Okay, let's see if they're going to draw it so I don't have to. Okay, because the denominator is 0 when x equals 0, the domain of f is all real numbers. That's where we usually begin. All real numbers except any that we have to leave off. And that would be x equals 0. Okay? And then they did this sort of chart here. They didn't do all the ones we did, but they did a lot of them. Okay? When x is equal to -1, they started on the negative side. I started on the positive. Then f of x is -1. When it was -1/2 or 0.5, it was -2. When it was -1/10, I said 1 over 10, but that's 1/10. -10, 100th, -100, 1,000th, -1,000. As x is getting closer to 0, this is going to negative infinity, which is not a number. It just gets much larger negatively forever. Okay? And why in the world they started this way, I think I sort of know. But it's backwards. I mean, you should have had this one that way and this one that way. I don't know. But they did 1 is 1, 0.5 is 2, 0.1 is 10, 100, 1,000. And the closer it gets to 0 from the right, that's why they did it. The f of x is going to positive infinity. Getting larger and larger and larger with no bound, without a bound to it. Okay. That makes sense? Okay, note that x approaches 0 from the left, f decreases without bound, like that. When from the right, it increases without bound. Okay? In contrast, x approaches 0 from the right, it increases without bound. So here's what the function looks like. The graph of f is shown here. Now what we didn't talk about was what happens when f gets larger, large positive numbers or large negative numbers. We'll get to that a little bit later, but here, as x approaches 0 from the positive side, it goes infinitely large. From the negative side, it goes infinitely small. And all those values were negative. All these values were positive. Okay? Now, we didn't go bigger numbers. When x equals 2, what is the value for f? X equals 2. What is f? Say again? 1 over 2, which is 1/2. Right? Okay. And when x is equal to 3? 1/3. 4? 10? 100? 1,000? 1,000? Getting closer and closer and closer to 0, but never reaching it. Right? So here, as it gets closer to 0, it goes infinitely large. As you go x infinitely large, it gets f of x goes closer to 0. Same thing here. As x gets closer to 0, f of x goes infinitely large negative, but as x gets infinitely large negative, f of x is becoming closer and closer to 0 from the minus side. Okay. Now, we aren't there yet, but let me just point out to you. The y-axis here we call a vertical asymptote because the function approaches it but never touches it in either direction. And the horizontal axis we call, the x-axis actually is a horizontal asymptote because in the long run, for very large positive or negative x's, that's where your function is going. So that becomes what we call a horizontal asymptote. Just like we did for polynomial functions, they always went to plus or minus infinity in the long run. Remember, we did that early on? But here, sometimes they'll go to plus or minus infinity, sometimes they'll go to some other number, like this one's going to 0. All right, now, there is a checkpoint at the bottom of page 166. Please do that one. It's a little bit more complicated problem, but still not very complicated, but it's not quite as obvious as that one. Now, let's talk about vertical and horizontal asymptotes. In example 1, and this is what I was just saying, as the behavior of f near x equals 0 is denoted as follows. Now, this looks sort of familiar, doesn't it? I usually write it the other way. I usually start, as x approaches 0 from the left-hand side. Now, before we were talking about end behavior, right? And I always said as x approaches either positive or negative infinity. Now we're approaching, let x approach your place where it can't happen, okay? Where you have to exclude it from the domain. And we'll let x approach that value 0 from the left-hand side. What is f doing? It's going to negative infinity. As x approaches that value from the right-hand side, f of x is going to positive infinity. So that's how we usually, you're already here, okay? That's how we refer to what's happening there. So this is a very similar format to what you saw with end behavior, okay? So this line, x equals 0, which it approaches from the left or from the right, but never reaches because x can't be 0, that line is called a vertical asymptote, okay? And the graph of f is shown here. Now this is how the book refers to it. Here's how I refer to it, okay? To me, this is just so much simpler, and it says it all. Let's go back to the actual function. Oh, here it is right here. F of x is equal to 1 over x. Let me get my pen back to black. Okay? Let me get it back to black. It won't go back to black. There it goes. Okay. As soon as I see this, here's what I like to write down. And we've been doing it before. The book never made us do it, but I think it's a good idea. As soon as I see this, I say x cannot equal 0. Right? Because that denominator cannot be 0. Okay? As soon as you write that down, this describes what the vertical asymptote is. X can't be that. So therefore, it'll never reach it from the left or from the right. It cannot equal 0. So there's your vertical asymptote. Okay? At x equals 0. Now, what I was saying before, and they show it on here, but we're going to talk about it on the next slide, is similarly, now with, again, let's think back. Polynomial equations, first thing we did was talk about end behavior. Where is the function going as x is larger and larger and larger? For polynomials, it's going to an infinity, one way or another. Sometimes that happens with rational functions, but sometimes it's going to fixed value. Here, as x is very, very large negatively, your f of x is going closer and closer to 0. From the negative side, but still closer to 0. Here, as x is larger and larger positive, your function is going closer and closer to 0. So we call that a horizontal asymptote. So that's why they said y is equal to 0 is a horizontal asymptote, x equals 0 is a vertical asymptote. Now notice, vertical asymptotes are always x equals something. Horizontal asymptotes are always y is equal to something. Okay, doesn't have to be 0, but it's something. Okay, making sense? A little bit. Okay, from that figure, this is what I said they were going to talk about next, but they showed it there. From that figure, you can see the graph also has a horizontal asymptote where line y is equal to 0, and what's happening there is sort of the reverse. For the vertical asymptote, you let the x get closer or closer to the value you can't have, the excluded value, And then you see what the y is doing, alpha of x is doing. Now, the horizontal asymptote is just like our end behavior. That's exactly what it is. As x goes to negative infinity, alpha of x is going to 0. Now, it's from the minus side, but who cares? And as alpha of x goes to positive infinity, alpha of x is still going to 0. From the plus side, but who cares? It's going to 0. So this is how we express that. It's, again, our end behavior. What's happening as x goes to positive and negative infinity? Now the answer is always an infinity. It could be another number. It could be an infinity. We don't know. You have to evaluate from the graph. Does that make sense? Okay. Any questions? Any place it doesn't make sense? All right. So here's the definitions of vertical and horizontal asymptotes. Now, again, when I do this, I identify where x is not equal to something. Like one of those places where x can't, the denominator can't be 0, that's identified when x is at some value, and I say x can't equal that. That's a vertical asymptote of the graph when f of x approaches either positive or negative infinity as x approaches that a from either the right or the left. Okay. The line y is equal to b is a horizontal asymptote of the graph when f approaches b as x approaches infinity, positive or negative infinity. If f is approaching the same value b going either way, that's called a horizontal asymptote. And eventually, as x approaches positive or negative infinity, the distance between the horizontal asymptote and the points on the graph must be approaching 0. They're getting closer and closer and closer. Now, here's a little difference between vertical and horizontal asymptotes. It's sort of an important difference. A vertical asymptote, the function can never, ever touch or cross it at all. It'll approach it, but never touch it. A horizontal asymptote, the function could cross it early on, but it's in the long run. That's the horizontal asymptote. So it can cross in the middle somewhere here, the horizontal asymptote, but in the long run, it's approaching, going closer and closer to it. Okay? So that's sort of a little difference between horizontal and vertical asymptote. Vertical asymptote, it just can never touch it because it can never make the denominator 0. All right. So here's some examples that are in your text also. Good, they gave you the functions. F of x is equal to 2x plus 1 over x plus 1. Is that a rational function? Yeah. A linear binomial, but a linear polynomial on the top, a linear polynomial on the bottom. Perfectly fine. Now, when you look at this, what can you, first thing your eye should go to is this. What can you tell me? From that denominator. What can denominators never be? 0. So you say x plus 1 cannot equal 0, right? And if you subtract 1 from both sides, you have. Yeah, I'll do it for you. Okay. This is how I suggest you approach these. As soon as you see that rational function, you say x plus 1 cannot equal 0, right? You can never divide by 0. The denominator can never be 0. Solve that equation. Ooh. Okay. Subtract 1 from both sides, and that gives you x cannot equal negative 1. And looky there. There's your vertical asymptote right there. Okay? X equal negative 1 with sound effects. Okay, right there. Function can never touch it. Never cross it. Ever. Okay. Now, they haven't gotten to the point here of telling you how you do the horizontal asymptote. That's how you do the vertical asymptote. Find that denominator, say it cannot equal 0, and then solve that. Find out what values will make that equal to 0. Okay? The horizontal asymptote, what is that? That's in the long run. when x is getting very, very big, large, negative, or positive, okay, in the long run, well, what happens then? Who cares about this? These terms, the leading terms, are going to take over your problem because that's where the x is at the largest power, right? So look at the ratio of the leading term. What's the ratio of those two? Just the leading term? 2x over x? 2. And look at here. Y is equal to 2 is your horizontal asymptote. Now, if this had been a 2x squared, and that would have been an x, it's going to go to infinity. Okay? This way. Okay? No horizontal asymptote. However, if this had been 2x up here, but an x squared down here, then the ratio there would be 2 over x. And as x goes to infinity, then that's going to 0. Right? Yeah. So then that's what happened in the first one, the horizontal axis. Y is equal to 0 was your thing. So I've just given you what we're going to hit a little bit later, but that's it. Vertical asymptote where the denominator cannot be 0, okay? Those values. Horizontal asymptote where the ratio of the leading terms to see what it is. And if it's a number like 2, that is your horizontal asymptote. If it's something over x, that's going to be x equals 0. I mean, y is equal to 0 is your horizontal asymptote. If it's something x over something, no horizontal asymptote. It's going to infinity in both directions. Okay. How about this one? F of x is equal to 4 over x squared plus 1. What's the first thing you look for? Your eyes zoom in on it. Where does it go? The denominator. And what can that never be? 0. Can x squared plus 1 ever be 0? No, because x squared is always positive. Add 1 to it, it's always positive. So yes, this has no vertical asymptote because that denominator is never going to be 0. Okay? How about the horizontal asymptote? Look at the ratio of the leading terms. 4 over x squared. As x goes to infinity, either direction, that's going to 0. Right? Going to 0. So sure enough, your horizontal asymptote is y is equal to 0. Let's let this one real quickly. What's the first thing you look for here? Oh, we'll pick that up. Is it time? Oh, how could it be? We just were beginning to have fun. Okay. Did we have enough for you to do any homework exercises here? Let me see. Quickly. Yes, you can do either 5 or 7 or both. They're both at Calc Chat. 7's at Calc View. And you can, I think you can start doing 9 through 15. They're all at Calc Chat. 15's at Calc View. We'll pick the rest of them later. Oh, quiz. Hey. Don't leave it blank on the quiz. Don't leave it blank on the quiz. Do something. Okay? Yeah, look at all the time. I have to mark those wrong. You're making me work too hard. Okay? Yeah, good deal. Okay? Get it to me Thursday with answers. Okay. I've got to see what happened to you. Oh, excellent. Look at that. Okay. What happened to yes, I must have missed something. Okay. Okay, I went to all that. Oh, I tried to get all that.
Do you have your, is it your regular office hours today?
Yeah, 11:15 to 3:15.
Is it okay if I come at 11:15
No.
and talk about schedule?
Okay. Actually, right at 11:15, I'll still be in 255. I'm usually up there so I can answer all their questions and usually do things like putting in attendance and stuff like that. So I'm usually up there for a little while. So I'm either 255 or 265. Check both places. And if not, I'm probably in the restroom. Just go back and wait you one of the places. Okay. All right. Good deal. And I recorded all that. That was good. Okay.